Thank you very much for being here today and welcome to this collaborative workshop. So today we're going to talk about new technology and new technology in precision forestry. And so we get the chance to have two passionate speakers with me today. So Kevin Toderel, which is from RMUS, he is the general manager, and Jean-François Prieur, who is the project manager at CERFO, and myself, Bastien Vandendaele, which is a researcher at NHRI. And so we built the workshop into three parts. And during the first part, Kevin is going to do a showcase of technology because we are going to show you how to use this technology. So the first part will be dedicated to a little showcase about UAV, mobile laser scanning, and other types of technologies. Then I will be taking the talk and talk about mobile laser scanning and UAV laser scanning and how to process the data from raw product to useful product. I will show you a lot of different interactive video. And then Jean-François Prieur is going to finish talking about species, AI, and different type of satellite data, more particularly the planetscope data, and how to process them to get a useful product for foresters. So I just let the talk to Kevin, and I give you the floor. Thank you very much.
Hello, everybody. Great to see you. Great to be here in Fredericton again. I always enjoy coming here. So just before I get into the presentation, how many of you, if I can get a quick show of hands, how many of you have flown any kind of UAV or remotely piloted aircraft in here? So we've got 3 or 4, a few of you. And then how many of you have used the technology in your operations at all? Anybody else? So a couple more, different things like that. Excellent. So one of the things that we do at RMUS, first of all, it stands for Rocky Mountain Unmanned Systems. And so we just say the letters just to shorten it up. That's what the branding gurus have told us. But we were originally founded in Salt Lake City, Utah. I run the Canadian business, which is headquartered out of Mississauga, and then we've got offices in Calgary and also Montreal. But what we do is we specialize certainly in drones, but we work with all kinds of remotely piloted vehicles. So that includes ground vehicles, underwater vehicles, wheeled vehicles, the spot quadruped, all kinds of different things like that. And really, we're starting to see within forestry this proliferation of aerial vehicles, but as this expands, really it's all about the sensing. And so really we're just looking at how we can deliver sensors to different places with different robots and different people in some cases to produce the kind of digitization that you guys are all talking about today. So I want to talk specifically what our background is, which is about some of the systems themselves. I myself am not a forester, nor am I a surveyor. We really look at enabling those technologies. So we're happy to talk about anything to do with setting up a program, different types of equipment, and then these gentlemen will talk about actually deploying it, and you'll see some really incredible data that they've collected. And I will give a shout out to these gentlemen. We've worked with them now for a couple of years, and really what they're doing is really groundbreaking throughout the world. Really, there's a couple of people doing some interesting stuff in other places, but it's really good to see Canada leading in those areas. So first I want to start out with the one that you see. This happens to be a Chinese-made product. This is the largest company in the world, DJI. These are very important just because this is a good example of a quadcopter. So this is what I would call a medium-sized quadcopter. So typically these things can hold about a 3-kilogram payload. And so this is the workhorse. This is the most common thing for sensor deployment. And so we have a number of different sensors. I'll talk a little bit about the one that's on here. But this is generally what is most commonly deployed in any kind of remote sensing and surveying. I'll show you a couple of other platforms, but this is the prime one. And so for quadcopters themselves, they're really focused on a few things, and really I think it's important and instructive to talk about the evolution of these products. And there's 3 really key areas. First of which is range. So when we started with these things, the radios would go, we might get 500 meters, okay? And now this one has a range in perfect conditions of 15 kilometers. So even though legally we can't yet fly beyond visual line of sight in most cases, which I'll talk about later, the technology exists to fly way further than we're actually allowed. Now, You guys work in the most challenging, or one of the most challenging RF radio communication environments, so you will not get 15 kilometers, depending on your elevations and things like that and how dense the canopy is, you'll probably get a few kilometers. But my point is, range is very, very important. And now we have opportunities with this with special antennas. You can fly over LTE, so cellular coverage, 5G, and in theory, you can get unlimited range. We've actually done these over Elon's system there. So Starlink, they've actually been deployed. So once again, even if you're in crazy remote areas with no cell coverage or anything like that, you can fly just as far as you need to fly, again with some permitting. So range is the second thing, and they've come a really, really long way with the range. The third thing is the modularity of the sensors. If you come up later, you can see a lot of these things are actually plug and play. So you can change for many different kinds of sensors. And so some sensors that'll work just by clicking, you have the opportunity to use multispectral sensors, so you can get some different bands for all kinds of applications there. You can deploy hyperspectral sensors. You can deploy just standard visual sensors where, depending on the resolution that you're going to need, anywhere from 24 to 120 megapixels. So if you're a megapixel geek like I am, 120 megapixels is pretty incredible. So to give you a sample of what you're doing with that is we have a project with CN Rail, and they want a 64-meter swath of track that they're going to fly at about 100 meters over, and they can get that with a single image from 100 meters. So pretty incredible. And so that would be for building orthomosaics and any kind of overhead mapping that you want to do, including some of the terrain. And then the third piece of that is what we have on here now, which is the LiDAR systems, and I'll talk about them in some detail because it's obviously very important to what we're doing here. But the LiDAR systems allow us to do more detailed scans, different point clouds, and most importantly, actually penetrate the canopy. So all of those things are really leading in and continuing to develop with this this particular system and other systems as well, this being the best example. The last piece of this is also for accuracy. So typically these are GPS or GNSS systems, and so initially we were getting plus or minus 10 meters. Now just with the standard one, you're down to about a meter. Just out of the box of absolute accuracy. They also connect to RTK base stations, so you can get precision. You can get within 1 centimeter of aerial accuracy, and when you correct for the cameras, about 3 centimeters of horizontal, maybe 5 centimeters vertical accuracy. And so a lot of them now, and this one will connect right into some of your existing, whether you have Trimble or Topcon or Leica base stations. So a lot of integration and a lot of accuracy improvements in the systems as well. And so again, we'll see some great examples with the different actual sensors that you're going to see there. So that's the quadcopter. So I'll go into a little bit about the sensors right now. So the first sensor is really a terrestrial kind of a LiDAR. And so how many of you have worked with LiDAR? Everybody or most? Yeah, well, a lot of hands out there. So this is just going to be your standard sort of survey LiDAR that you're going to fly, typically anywhere from 40 to 100 meters. Your speed is going to vary depending on what your accuracy levels. This one is pretty solid. So again, approximately, Bastien will talk about exactly what they got, but the spec is 3 to 5 centimeters again, absolute. And that is really going to create your point clouds. And so there's a wide variety and a huge cost delta for how much accuracy you're ultimately going to need. And so a lot of these things, it's good to test them out, because often you don't need the expense of of what you're getting for accuracy. For example, this one, if memory serves, is about $30,000, and for most people, that's going to give you an appropriate level of accuracy. You can spend $200,000 on the same sensor and get slightly better accuracy, possibly a more dense point cloud. But again, that's going to really depend on your own individual needs. And the background of these is really, when we look at them, we want as simple a workflow as we can possibly get. And so that's going to have a huge impact as well on what system you're going to choose. And so I guess my broader point is there's a number of different systems that you can deploy, and again, you'll see some things there. And so typically these have been deployed on the aircraft. So that's a terrestrial. The second one is this one I'm holding up right here, and so this is what we call a SLAM system, and so this one, essentially what the SLAM systems do is they simultaneously scan and map. And so the real power of them is while they're scanning, they can actually be used for navigation. And so this particular system, it's by Emerson, it's called HoverMap. And so what that system does is, this actually can tie into the system and allow, I'm going to air quote it, autonomous or semi-autonomous flight. And so what that means is you can actually navigate by putting a 3D waypoint on. You can actually tap that on a touchscreen, and it will find its best way to navigate. And so the technology was actually designed for underground mapping in mines, for stopes and things like that. It has been tested with, I'm going to say, moderate success in the forestry environment. It has actually been done. But it's far from reliable. The point is, it'll get better. So if you can picture being able to, depending on the density of your forest, being able to actually fly this under the canopy in the forest and have it navigate through there. There are some videos of this happening online that are quite spectacular, and you'll see some of those data sets that we're taking with the scanner handheld. But if that can be done autonomously, you're not going to be limited to the speed that you're going to walk, and you'll have significantly more range. And so again, those are actively building a map that's used for navigation as you go through. And so typically, and how Bastien and his team have done it, it's a hand scan. You're just going to walk it, and you can see it's a 360 scanner. So it'll go in this room or any kind of similar. You're probably going to get about 1 centimeter of accuracy with this. In some cases, even a little better, depending on how close you are to some of the trees. But these are really incredible ones, and these are roughly, there's a few different models, but just the handhelds are somewhere in the $30,000 to $60,000 range. And then when we get into the systems on there for full autonomy, we're talking with EDU licenses, you're somewhere around 75 to 80,000. This is all Canadian dollars. I'm Canadian, so I wouldn't hit you with whatever the exchange rate is today. So anyway, quite fascinating on the technologies and the multi-use. I will add on this one, if you come up and see, there's actually sensors all the way around above and below this. And so that's not for autonomous flight, but it does do well with large optical object avoidance. So it won't let you crash into walls and things like that. It's not nearly as sophisticated as the SLAM LiDAR system. So it's not, forestry approved at this point. But if it continues to get better, it's really the same system that Tesla's using with the visual sensing. So there's some possibilities there. So I think right now it's not going to be possible, but I think we're within a 3-year window of being able to operate more or less autonomously under the canopy. So I'll let your minds kind of percolate on that as well. And so this is just another option for the handheld scanner. I just want to put this in. So this is an example of something that was done underground. And so the way that's actually flown is we have someone also underground but sitting at the top of the stope, and that's all done completely with no visual line of sight to the aircraft. And essentially 3D waypoints, it's going to send it to a point, it's going to get a scan, they're going to say, oh, there's another stope that's branching, another tunnel going the other way. They're going to hit a waypoint, it's going to navigate there by itself, build the map as it navigates, come back in, and then they're going to continue to do that. So that probably took them, I don't know, probably 15 flights to get that particular map, especially when they don't know. But in theory, no visual line of sight, no visuals are necessary, and you have a complete scan. So I'll change gears a little bit here. And so this has traditionally been the workhorse of some of the inspections. There's also fixed wing platforms, and if we think of this as more like a helicopter, Delta Quad is a good example. You can actually see one, I saw it out there, there's an orange one there, the wing chart, great platform as well. But these are what we call fixed wing VTOL, so vertical takeoff and landing. And so these are very powerful aircraft because you're able to, take off without a runway like a helicopter, and they will transition over into more flying like an airplane. So that does a few things for you. One is it flies potentially higher, it flies much faster. These might be, say, 40 to 60 kilometers an hour. The fixed wings can get up to 100 kilometers an hour, and it flies typically for much longer. So flight time on this is about 40 minutes. Probably, what were you getting, like 25 minutes with that, Bastien?
Yeah, but 30.
Okay, good. So 30 minutes with that, and then the fixed wings can get into the 90 minutes plus range, and I'll show you almost significant range. So, as we start to talk about the fixed wing platforms, until very recently, the challenge we had with those platforms was they were great for really large areas, but we were limited to photogrammetry. So it was limited to visual sensors in terms of what we could do. So it was excellent if we wanted to do orthomosaics of really large areas and terrain as well. And then obviously we didn't have any penetration to get underneath the canopy for additional detail. So it was really good for overhead shots. And so this particular one is a Dutch-made product called the Delta Quad. And so we've seen with this initial one, very low cost to get involved. It's around 30,000 Canadian, but 61 megapixel sensor, so you can get some serious detail. Now, the one we're really excited about, which we've just come back from testing, is the new EVO. And so the EVO is slightly bigger. But the interesting thing is they've managed to fully integrate a yellow scan LiDAR into that. And so yellow scan, for those of you who don't know, it's a very high quality French-made system. And it has not only excellent quality, but it has significant penetration advantages to get through the canopy. And so that's one of the things about the LiDAR is, without going too technically, when you have multiple returns, you're able to get through the canopy and get right down to even getting the terrain underneath. So for your applications, you'll see a lot of detail that maybe you wouldn't see with regular scanners without having to go to the handheld. So again, Bastien and I will talk about some of that after. The interesting thing about this platform, which really kind of changes everything, is 4-hour flight time. 4-hour flight time. And so the first one I showed you with the 90-minute flight time, that will cover about 1,200 hectares in one flight. So with this one, it's going to be 2 and a bit x that. So it could be close to 3,000 hectares in a single flight. Now, our challenge has been in the past, what I talked about is we've got to keep these things in visual line of sight. One of the advantages that you all have, which is really important, is Transport Canada and the FAA in the US, for those of us that are coming up from the south, are really working to enable BV loss beyond visual line of sight operations. And so whenever they're looking at issuing waivers, or here we call it a special flight operations certificate, whenever they're looking at that, they're looking at risk levels. And so you have one of the least risky mission profiles possible. And so we've just in Canada come up with a new draft of the new regulations that will take place. They'll kick in April 2025. And then that will make it very easy for you to be able to do those kinds of missions with no additional permitting. You'll have to have some training, obviously, but strictly no permitting. And in the meantime, they're being very aggressive in trying to improve these kinds of missions. So I believe that you guys will be one of the real pioneers in doing beyond visual line of sight. So now we get rid of the biggest restriction that we have with these, which is going to be how far we can fly them, and we can just cover like huge areas of territory depending on what kind of data we're collecting. So these are, as I said, very, very, very exciting, and we are anxious to get some of these testing and see what kind of data sets we can get with the LiDAR. So I think next year, I hope we do this every year, but the next time we'll have Bastien, I think we'll have some more data sets with that as well. And so that's something we're looking forward to doing as well. And the last thing I'll show you just before I quickly pass it along to Bastien is this is a new technology. One of the things we're moving towards is autonomy. I'm unclear on how and if this will have an effect on your given businesses, but it's going to have a huge effect on UAVs overall. But essentially, one of the things that we see, particularly on our infrastructure side of our business, is this move to autonomy. And so what these drone-in-a-boxes do is it functions as a control station and a recharging station for these exact same types of aircraft. And so essentially what you can do with that is you can take off and land and run pre-programmed missions either without any pilot intervention on site, and in theory you can manage multiple boxes from a remote location as long as you have some kind of either satellite, LTE, or network connectivity. And so for a lot of these things, this can be present at a remote site. Again, for us on the infrastructure side, there's, many of our partners are looking at this as anything remote that they have to monitor, whether it's a substation or something where they need it, so remote fields. And the box just sits there, it's weatherproof, and whenever they need it, they can operate it centrally to get a look at what they need. And then they can also program it to collect data on regular intervals. So that was something I wanted to share. So this is one of our US partners there that works with a bigger drone. And then this is a DJI product, which is a slightly smaller drone. And so the larger ones we'll be able to deploy with whatever sensor we want, LiDAR, and then the smaller ones will strictly be either just a mapping sensor or some kind of a multispectral type sensor. Excellent. So I thank you for listening. I'll be around if you have any specific technical questions. But now I know you're going to get into the good stuff here, and Bastien's going to show you some data. So thank you.